carbohydrates. Categorization. I like this better. We're doing categorization right now. Well, there are the monos, and we call these monosaccharide, right? And these are our simple sugars. And these simple sugars can be also our disaccharides. They also can be considered. Can I just abbreviate saccharide like this now? Is that okay? All right. So the disaccharide also can be in this same category of simple sugars. Basically, we're talking about anything less than 3 sugars. We're going to call simple sugars, meaning they probably don't have much fiber, or if they do, it's not very hefty. Fruits have fiber, and they're disaccharides or monosaccharides. So they are still in this category, yet they have fiber. So they kind of fight the system. After that, we start going by the numbers. I'm sure you guys have all had this. How many people have had OChem? Oh my gosh. All right, then this is going to be a repeat for most of y'all. Thank you. It's not required, but hey. All right, so we've got trioses. So how many sugars do trioses have? 3. So those are our 3s. And then what are our 4s? Tetros. And our 5s. Our pentos. And our 6s. Relax, Whitney. I love you. There are other people in here. All right. And then after that, we pretty much call them oligosaccharides or much larger molecules. So after we get to, we would call all of these complex carbohydrates, or we would call these complex carbohydrates. Complex, and I'm going to abbreviate carbohydrates this way. All right? CHO, that's carbohydrates. We're going to call these complex carbohydrates, or you could also call them, instead of monosaccharides and simple sugars, we could call them complex carbohydrates or polysaccharides. I should have done it. Monosaccharide, simple sugars, polysaccharide, complex carbohydrates. That would be the correct on your SAT. Monosaccharide is to simple sugar, as polysaccharide is to, there you go. Do you remember that section on your SAT?
Yes.
Oh my goodness. All right, so that pretty much is the categorization. How we categorize the nomenclature. What do we call our carbohydrates? And we'll be talking about some names of carbohydrates that we're going to be putting in those categories. All right? You probably already know many of the hexoses, right? That would be your glucose, your galactose, your fructose, and then of course the pentoses, which would be your ribose, right? Your xylulose and arabinose, which are really important in food science. But let's talk about some of the characteristics of carbohydrates. Why are they so important? Besides metabolism, it's really hard for me not to teach them the metabolic part of this, because that's really what I've taught for years and years and years. But we're supposed to be talking about the food science. So the characteristics would be, first of all, they have a sweet taste. Well, what the heck is sweet, and who decided to call it sweet? You know what I'm saying? So someone somewhere had to decide that that was a pleasurable taste to the human, and it made them feel good, and they had energy after eating it. And hey, guess what? You didn't die after eating it. So, there's something called the omnivore's paradox, that as omnivores, we can eat a huge variety of food. But through our history, the millennia of our evolution, the people who were more likely to like a wide variety and want to try things were more likely to die than the person who really stayed conservative and only ate certain things. But that's the omnivore's paradox, because we're made to survive through all these different times of trials during our evolutionary, during the millennia, right? Because we can eat all these different things. And yet the one who does has a greater statistical probability of dying. Do you see what I'm getting at? It's a paradox. That's what a paradox means. Both things cannot be true at the same time, yet they are. All right, so people or food that tasted bitter or sour to us tend to be poisonous to human beings. Therefore, the person who tried it died, and the one standing next to them said, "Oh, we won't eat that." Someone write down what this looks like, and now in our lexicon from now on, we will not eat this plant. Now this one, Sally, come try this one. It tastes sweet. She did not die. Therefore, things that taste like this one that did not kill her, we are going to classify as good for us. Do you see what I'm getting at? And that is how we have evolved over time to be carbohydrate needers for our energy. I'm not talking about the sugar they put in the bun at McDonald's. I'm talking about carbohydrates, would encompass a huge amount of a huge group. So other characteristics besides that make it important is that ratio. That ratio that is similar to water. Ease of solubility. That's huge. If it didn't dissolve in water, then our watery solvents, then we would have a real problem. It contributes to the mouthfeel. This goes back to the organoleptics that we've talked about before. What's organoleptics again?
Sensory targeting.
Sensory. It's our sensory thing. So this mouthfeel, when you put something in your mouth, does it crumble? Or when you put it in your mouth, is it hard? Which, for a certain thing, it should be, right? You don't want to put a piece of steak in your mouth and it crumbles, right? So the mouthfeel of what you expect a certain food to do is hugely important for its palatability and therefore its success as a food for us. Sugar, carbohydrate, is one of the things that controls the mouthfeel of our food. And that's why some foods you found don't taste or feel the same way that they're supposed to. Browning, this browning that we expect, luckily, it occurs at high temperatures. And I'm going to abbreviate high like that, even though I can't stand it when people do that on signage. But for here, again, let me know if my abbreviations are confusing you. And that T is temperature. So this browning at high temperatures, in other words, if something browned at too low a temperature, then it wouldn't get thoroughly cooked before it was really brown. By the time it was cooked, it might look too brown to you. You see what I'm getting at? So it's fairly important, the temperature of the browning. And you're going to learn, especially in the lab, we learn about how temperature impacts browning, like we're making cookies today. And fudge. All right, so browning. Also, there's something about the volume contribution. For example, when people first started deciding, hey, you can cook with equal, and there's going to be no calories. Let's cook with equal. Let's cook with aspartame. And I was one of them. It's like, yeah, this is great. I only need 2 packages of equal to equal, a half a cup of sugar. Well, what's the problem with that when I started making the batter? The volume was off. In other words, you need the volume of that sugar. So I've got all this flour, and I'm stirring in the baking soda, I'm stirring in the salt, and I'm stirring in 2 packages of equal. How much volume do I have to actually make batter to make cookies? Do you see the point I'm making? So the fact that sugar has volume, and that's what now our people have now invented, equal, sweet and low, not sweet and low, but Splenda, Truvia, that has the volume of sugar, so they've put it on another matrix. See, this is food science, finding the matrix that works. So there is another matrix that's being used to create the volume that sugar naturally contributes to the recipe. I think this is fascinating, don't you? Okay, and then there is 6. If we're talking specifically about starch, then we're talking about thickening. In fact, let me redo that. Let's write down thickening. It has a thickening capacity, and put in parentheses starch, one of the characteristics of carbohydrates. Then the, texture modification. And then put underneath in parentheses cellulose. cellulose, the stuff that you can't really digest, but it adds a texture to food, doesn't it? Even though you can't digest it, you can certainly chew it, and it's going to add some texture, or maybe some harshness or a rough feel that you expect from certain foods, right? And then there is, there's a thickening of starch, and let's add to that one. Let's add up here pectins. And the reason pectins and gums, these are non-caloric. Naturally occurring, and they are non-caloric. Therefore, these are the things that some of our products are adding to them. So when an ice cream is trying to make an ice cream that is thick, that doesn't have the calories of this Breyer's ice cream that use just all natural starch, blah, 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 blah. The one that's got the gum and pectin in it's lower calories because they have done this for you. Not a bad thing. This is stuff that we still is in our food, and it's natural. It's naturally found in fruits and vegetables, etc. Okay, so as far as, I pushed my pentoses up there. Okay, I want you to go underneath your pentoses, and I want you to write down these three that are the most important for food. Okay, are you ready? I'll write them on the board for you. Ribose, I kind of mentioned them already, but I want you to have them in your notes. Arabinose and xylose. You recognize some of these because, like xylose, the food manufacturers have taken this 5-carbon sugar and they've made an alcohol of it and call it xylitol. That is an alcohol sweetener that has got the sweetening capacity of xylose without the calories. Therefore, it's considered a non-caloric sweetener, and it is all I've done is taken one of these carbons and made it an alcohol instead of a sugar. Isn't that fascinating? All right, so these are the 5. You don't have to be able to draw them, but you certainly need to be able to know that those are 5-carbon sugars. Yes, sir? Well, because in order for it to be a calorie contributor, that means it can help make energy, correct? ATP. And once you've changed the structure of that, it can no longer enter the glycolytic pathway. It really is that simple. And it does it at the, here we go, are you ready? Hold on to your seats. The remember PFK step? The most highly regulated step? Fructose 1,2, bisphosphatase, and all of those stuff, 1 and 2, remember PFK 1 and 2, all that stuff? The alcohol impacts that reaction and thereby renders it non-functional. Yes?
Do you think that there's any negative impacts for converting it to an alcohol and digesting it that way?
Well, that's an interesting question, and that's one that I do want to consider. We are going to get to sweeteners and spend a little bit more time with that. I think, as always, time will tell. But my personal experience working with diabetics and overweight, which as a dietitian, before I came back to get my doctorate, and I was in private practice, that's all you see. That is what the world is. I used to do, I get to do hyperlipidemia and other stuff, but not anymore. It's basically overweight, obesity, diabetes. And I find that those things are actually lifesavers. Lifesavers. Because I've got the people who want the sweet taste, and they can have a diet soda and it takes care of it. I recommend water instead, clearly, but as a dietitian, that's not what you do. You don't come in and say, your diet sucks. Okay, I want you to throw it away, and now here's the good one. That doesn't happen. What you do is you say, how are you eating? There are a few things that we can change that are going to make a big difference, but basically, you're still going to continue eating the same way, which in your head you're going, this diet sucks, we're going to get rid of it totally, but I'm not letting this person know that, and we're going to do it in a stepwise manner, so that they're involved and they're invested, So those are the things, but that is a great question. And I'd like you, by the time we're through us talking about some of these sweeteners, I'd like to ask you that question. See what you think. Yes, sir?
I've heard that some people have GI problems because of something like stevia. Do you know what causes?
Well, actually, some of the GI problems that people claim to have had, when these people are collected, like I'm thinking most especially about Equal. When they collected the people who were complaining of GI problems or headaches, and they did the RCT. Gold standard, what is it? Randomized controlled trial. So therefore, it's the gold standard where we've got double masked. We don't say blinded anymore internationally because people really thought Americans were coming in and blinding their people. We say double masked. We have bad reputation in some countries, y'all. All right, so double masked. It was randomized, meaning nobody knew what group they were in, et cetera, et cetera. And they found that there was no validity to any of these claims, that the people who claimed a GI distress or headaches actually had them with the placebo just as often or more often than when they had the actual product. So therefore, from these studies, there has come a certain understanding that there are what we call cluster behavior. There are people who tend to have headaches. And there are certain things they're going to eat or drink that are going to seem to, they think, are causal to these headaches, when actually real science, evidence-based, shows that it's not true. Okay? So, yeah. Yes, sir?
So you said earlier that the ribose, ribose, and xylose were all under the pentose category, right?
Yes, sir.
But those are all like single sugars, correct? Like.
Oh, I see what you're saying. I see what you're saying. Okay, you're right. Thank you. Thank you. I have classified these larger sugars as complex carbohydrates, where I was thinking that these were in chains, because most of them don't really exist singular. So thank you for pointing that out. He's pointing out that me classifying just the larger molecules as complex was incorrect. Actually, it would be chains of those larger molecules. Do you understand that? Thank you very much for clarifying that. And I will be going into that in just a minute. Okay? Awesome. Yeah, I'm so glad you're in this class. You keep me on track every time. Yes?
So would those three be considered monosaccharides then? Or would they split?
Yes, they're all monosaccharides unless they're in chains. It's a good point. You can get rid of that whole thing. The complex carbohydrates would be the polysaccharides or the oligosaccharides, not the pentose whatever, okay, even though those usually exist in those chains. Does everybody understand what I'm saying? Okay, yes.
So what you're saying is the monosaccharides and disaccharides, they don't exist within chains in food? Or they do?
Well, I'm talking about those as singular ones. In other words, glucose can be a monosaccharide, right? But it very rarely exists as glucose unless, like, Stokely Van Camp has made it as Gatorade, right? Fructose, however, is the one exception that can exist as a monosaccharide and yet still have fiber in it. In dietetics, we call it a complex carbohydrate. I know. Am I just confusing you even more? Let's keep it to mono, di, poly, oligo. How's that? Does everyone know what oligo means? Massively big. So let's keep it to, and I'm so glad you guys are the nomenclature. Let's keep it to mono, di, poly, and oligo. And the simple and complex is being thought about in chemistry and dietetics. We think complex carbohydrates are anything that pretty much has fiber, and that would include fruit, which is a monosaccharide. But basically, in chemistry, a complex carbohydrate has to be 3 or more. Okay? Yes?
My understanding of an oligosaccharide is like a shorter chain, like 3 to 10.
Well, oligosaccharide is bigger than any of the ones up there. It's the biggest of the group. Would you agree?
Oh, I thought it was like simple oligo and then poly.
It's mono, di, poly, oligo. Oligo is longer. Well, poly is all of them, isn't it? Once it's more than 1 or 2. Oh, well, you guys who've had OChem. I remember now why. Okay. All right. So you're saying in the text, is the text say this?
Yeah.
Yes.
That oligo, it goes here?
It's 3 to 10.
And then what's poly? All of them? Thing is, I called something that's 3 a polysaccharide. So that's incorrect, so I should have been referring to as oligosaccharides all that time?
I think all oligosaccharides
Are polysaccharides? You're going to clear this up for me?
Yeah, so from my understanding, a polysaccharide is somewhat of a repeating saccharide, which means that there's basically many polysaccharides, and the logo does not have that.
It's like 10 singular ones?
Like
3 to 10?
It could be different ones, but it doesn't have to have that.
It doesn't have to be repeating, whereas poly has to be repeating. My gosh, where'd you guys learn this? Is this from OChem?
Yeah.
What is it from? Biochem. I don't teach this in biochem. That's incredible. Good for you. All right, so according, what's your name, dude? What?
Martin?
Martin. According to Martin, I'm getting to trust Martin. The oligo, he's saying, is 3 to 10 saccharides or sugars that don't necessarily have to be repeating. They could be all singular, but they can. Whereas poly is a longer chain that has to be repeating. Does that sound right to you guys? That's great. Yeah.
Someone asked about like the negative effects of making xylose.
Into xylose, yeah.
But I heard that bacteria can't metabolize it the same, so it's not as common in a lot of like dental gums and stuff, dental like candies.
Okay, so as far as the sugars go and the artificial sweeteners, we're going to get to that. If we can save those questions till we actually get to that at the end, I appreciate your interest, I think, and it's where a lot of the interest should be, I think. Clearly, we need to get through some of this basic stuff for my sake. Yeah, there was another question back there. Was it about artificial sweeteners? We can wait on that? Okay. Woo! All right then. So we got this straight. And I don't have any of this in my notes. I want you to know that. I don't have any, I just have a list. So I'm sorry I didn't write any of that down. I thought it was so well understood by me. All right. So now we're going to talk about the ones that are the most important, not only in metabolism, but in our foods. And that is the hexoses, okay, or the 6 carbon molecules. And that is glucose, galactose, and fructose. And I write these 3-letter nomenclature on the board because this is the international symbols. All right, and if you use, like, for example, GLU for glucose, what is GLU really? Glutamate. It's glutamate, exactly right. So it's important that you use the correct 3-letter symbols so that you can communicate. So glucose, and these are the 3. From now on, I'm going to be drawing structures. Yes, you must know them, and you must be able to draw them. All right, so now we could do the Fisher projections, or we're going to do the Hayworth. I like them. They speak more. Sugars really do exist as circular or cyclic beings, okay? So the Fisher projections were created. They were the first ones to sort of be able to understand the stereochemistry around that carbon molecule. But we're going to use the Hayworth projections, and I'm hoping that everybody understands that these intersections are where carbon molecules exist, and it means that this carbon molecule, this carbon molecule, and this carbon molecule share this oxygen. That's how they cycled up or circled up, okay? And then I'm going to be drawing lines that show the hydroxyl group orientation. And of course, we're looking at something that is really 3-dimensional, and we're putting on a 2-dimensional. So that alpha and beta positioning really is in or out of the plane, all right? But basically, the way we're going to represent it is up or down. The down position is called alpha, and the up position is called beta. Exactly right. Sort of a little counterintuitive. As alphabet, we like to go up, down, don't we? But it's the exact opposite in stereochemistry. This distinction is extremely important. This alpha D, we eat D glucose, we metabolize the D, which way the light turns, D or L. And this alpha is extremely important in our metabolism, but also in all the sugars that we eat. It must be this in this position. And so the way I remember it is I say down, down, up, down. I'm a musician. So I tend to put little songs to things, okay? Down, down, up, down. That is our glucose. Did you have a question? What?
Can it also be alpha, the H2CO, which is down, the O, which is up? Because alpha is like the O, which is down.
Okay. Well, what we're talking about, I encourage you guys, I love that you guys, you know, clearly you know quite a bit, but I encourage you guys to let go of a little bit of some of your, let go just a little bit and let me, and you know what I mean? Instead of, I know that as a student, we're always trying to find the one that doesn't fit, right? Trying to find the counter rule. But let me get through this just a little bit, and then maybe okay. We're talking about the anomeric carbon. What is the anomeric carbon? What does it mean? Chiral. What is a chiral carbon? Yes.
It's one that's attached to 4 different things.
Thank you. That's perfect. Exactly. Well, so find the anomeric carbon, the one that's attached to 4 different things. Let's see. This one's attached to no. It's got 2 hydrogens on it. This one, 2 carbons, 2 carbons, 2 carbons. This one is the only one that's attached to a carbon, an oxygen, a hydroxyl group, and there's an understood hydrogen, right? Okay, we don't write the hydrogen on there, they're understood. So this is the anomeric carbon. Anomeric or chiral is another word that is used. They spin the light differently when they are attached to 4 different things. Therefore, when we get to our sugars, that's how we define how we're going to number our carbons. So the anomeric carbon is carbon 1. So this is carbon 1. This is carbon 2, 3, 4, 5, and 6. So in answer to your previous question, if we were going to name this molecule by using the 6th carbon, and it was, you see what I'm saying? So we're naming this molecule by using the 1st carbon. So this is an alpha D glucose. An alpha D glucose. All right? Now, because it's an alpha D glucose, that means we can do this. We can combine it with another alpha D. What's wrong? What's wrong? I hear a whispering. What? Okay, the D and the L, those are used to just describe the way the light turns, right or left, essentially. All right? And it's just fairly important that you understand that D is what we eat, it's what we metabolize. All right, so this glucose plus another alpha D glucose. And by the way I'm writing this up here, it doesn't have to be like that. You might see some textbooks do it this way. But it bothers me as a biochemist because I want to see the OH on the carbon. That just seems to me make more sense. All right, so we have 2 glucoses. We're going to make a disaccharide. So to combine these 2 glucoses, we need to condense this molecule, don't we? We need to condense the molecule. What is condensation? What are you losing? What is implied with condensation, condensing? We're going to lose a water molecule. It doesn't matter how you do this, but you're going to lose a water. And by doing so, you have performed a condensation reaction. A condensation reaction. And therefore, you're going to get a molecule that looks like this. See this? So what we have formed right here You notice the angle of this, because in the 4 position of glucose, the oxygen, the hydroxyl group, was in the alpha position as well, wasn't it? So therefore, the alpha position of the 1 and the alpha position of the 4 of glucose allows us to make this molecule. What have I just made, by the way? It's essentially maltose. 2 glucose molecules, but it's the beginning of something we call amylose. Amylose is usually longer strings of this. So basically, and I didn't finish this down. I didn't finish this. There. So you see how the string could continue, don't you? Okay, and this is this bond right here, we're going to call an alpha 1 to 4 glycosidic bond. An alpha 1 to 4. You notice that arrow there? In chemistry, that means something to us. It's not 1, 4, because that essentially implies 1 through 4, doesn't it? Or 1, comma 4. That means 1 and 4. The arrow implies a 1 to 4 connection. So this arrow is very important, and that's the way it should be written. An alpha 1 to 4 glycosidic bond. It's important you get this, because you need to understand the alpha 1 to 6 glycosidic bond. So let's say that we then continue with those molecules, with strings. And these are all alpha 1 to 4 glycosidic bonds of glucose, right? This long string that I'm drawing of alpha 1 to 4 is called what? Amylose. And this is amylose. And this is how our body stores sugar. Is this an efficient way to store sugar? Let's say I told you guys, every one of you had to hold hands and make a line. And this line had to be straight, but you had to stay in this room. Would you be successful with that?
No.
He says no. You would have to curve, right? But also, even if you curve, let's say we filled up this room 2 or 3 times, eventually, even if you were making circles, would you notice all the wasted space? Basically, what we have learned to do, anywhere from 8 to 10, is we make a branch. It's called an alpha 1 to 6 glycosidic bond. And that means our glucose is what it looks like is efficient at this. This one, I should have drawn this over here. But anyway, the bond would be like this, but make it a straight line, okay? I know, I'm not an artist at all. Let's say, here we go, we'll put it over here. There. Okay, we've got a alpha 1 to 6. So it is looking at the 1 carbon of this one and the 6 carbon of that one. All right? And that makes this branch that now can go, and so it makes a 90-degree angle, and now we are back to alpha 1 to 6 bonds. And then once we get down to 8, it does it again. We can do another alpha 1 to 6, and we create branches on the branches, on the branches, on the branches, 1, 2, 3, 4, 5, 6, 7, 8, and we keep going and going and going. It's this ability to make branches and go alpha 1, 6 glycosidic bonds that allows us to create what in our bodies? Glycogen, good. What we've drawn on the board is glycogen. This is glycogen, and this is how we store our carbohydrates. Extremely important that you get is a string of alpha 1 to 4 glycosidic bonds, and every 8 to 10, there's an alpha 1 to 6 branch, that one branch, and then a continuation of alpha 1 to 4. Why is this important? Because we're about to compare this to plants, to how plants do this. All right, so we have strings of this glucose, right? And by the way, with the first disaccharide of glucose that I drew, I said it was maltose. Remember that? That is one of the most important. It's one of the 3 big disaccharides in metabolism and in our food. Where do we get maltose? So 2 carbons. If it's glucose plus glucose, this equals maltose. And maltose is found in grains. It is our grain sugar. It's where you get your beer. It's where you get a lot of the sweeteners in your grains. That's why wheat can be relatively sweet. Galactose plus glucose equals lactose, which is milk sugar. And the way you remember this, glucose is in all 3 of our major disaccharides. The way you remember this is gallon of milk. I know you'll thank me forever. I have these tricks out the kazoo. Gallon of milk, and that's how you remember that it's glucose plus galactose. And then fructose plus the glucose, it's the last one. What is it?
Sucrose.
It's sucrose. And sucrose comes from where?
Fruit.
We call it table sugar, but does it grow up as table sugar out of the ground? Well, it used to be sugar cane in Louisiana and Texas and Florida and Hawaii, but sugar cane is a huge water hog. And as it became more expensive for land and water, everyone switched. Well, there's still some sugar cane. I grew up sucking on. Have you ever bought a little piece of sugar cane and sucked on it? If you go down south of the border, you can still get that quite a bit, or over actually in the Philippines. But what about the main sugar source, our main sugar source? What are we using now? Beets. Thank you. Sugar beet. The sugar beet. Absolutely right. Sugar beet growing all over the place. And you can get sucrose from your sugar beet. Absolutely right. Huge moneymaker in Louisiana. Okay. So I want to get to the structure of these in just a minute. Does everyone understand, though, this glycolytic linkage? Everyone understand that as a glycolytic bond, right? And how would you call that? If I said, draw 2 glucoses with an alpha 1 to 6 glycosidic bond, could you do it? If I said, add an alpha 1 to 6 glycosidic bond, could you do that? What if I said, draw a beta 1 to 4 glycosidic bond? Could you do that? All right. So we've got glucose. And let's pretend instead of alpha, it's beta right here. And it's going to try to bond with another, and it doesn't matter if this is an alpha 1 to 6 or not. Let's just say that it happens to be another beta. But it doesn't really matter unless we're going to continue on the chain. Down, down, up, down. Okay, we need to make a glycosidic bond. A condensation reaction, right? So what we would need to do is, again, lose a water, right? We lose a water. And now this bond between those two looks like this. I hope you're practicing drawing these too. All right, so this is what the bond looks like now. And so this is called the beta 1 to 4 glycosidic bond. This is something that we cannot digest. We do not available to do this. So therefore, this is what we call cellulose. This is in plants. This is the linkage in plants. Plants have the beta glucose, and we use the alpha. Yes?
Where does the extra carbon come from between the two rings?
Have I drawn it wrong?
Where does some of the two?
I think it's just a bonds on it.
We just have to draw it up.
What now?
I think there's.
Oh, these are bonds. Those aren't bonds. I mean, there's no carbons there.
Yeah.
So it should
Okay?
be a straight line?
No, it wouldn't be a straight line.
It would stop.
It just curved.
Boy, you guys are tough. This is I've drawn it forever. But yeah, these are not implied bonds. But no, it's not a straight line. It's an actual, and I'm sure that there's some reason that this is this way. Okay. But yes, no, thank you though. Thanks for clarifying that. That is not meant to be bonds. Those are just funky little, I'm trying to see how if I have any pictures. No, the pictures in your text and the way I've seen them my entire life are exactly how I've drawn them. So I can't explain that. But it goes up and then down and then, yeah. Okay? Fun stuff. Boy, this is great. Now this is honestly good. You guys are keeping me on my toes. So we have about 5 minutes left, and I promised, and we're going to continue with this. We're going to get into actually cellulose and amylopectin, and we need to talk about those things. But you're not going to be required to know any other structures besides, I'll finish this. In fact, we'll start here next time. You're going to need to be able to draw glucose, galactose, and fructose, and at least one alpha 1 to 4 glycosidic bond, and circle the bond. That's about as complicated as we're going to get in here, but you will need to be able to do essentially what I've shown you on the board right now. But I wanted to illustrate to you the difference in viewing this structure of the alpha linkage and the beta linkage, and how different that is, okay, and why there's cellulose that we cannot digest. But I want to take these last few minutes. I promised some people in this class that what I do for most of my classes, I give you 5 minutes of immunity, and you get to ask me any question you want about nutrition that has nothing to do. It can have something to do, but it doesn't have to have anything to do with what we're talking about. It could be any nutrition question. The one thing I ask, the caveat, you don't put your notebooks and stuff away, that you're not getting ready to go yet, because someone may ask you a question that you may actually want to write down, and it gives a little more gravitas to this, okay? So please don't start putting things away just yet. All right, question.
I've been hearing that activated charcoal could help with hangovers. What do you think about that?
Activated charcoal can what?
Help with hangovers. What do you think about
With hangovers. And so did they give you any theory as to why that is?
Well, activated charcoal is used in the ER to bond with charged particles such as drugs and other toxins. And I know that it can be harmful for like some drugs that you may be taking, but those tears say that it
So when she's talking about the charcoal being used to bond other drugs and things, what is she talking about? So what's the word we're looking for? We're looking for chelation. Charcoal has the ability to chelate, especially with heavy metals, right? And some of those things are found in some of the drugs, especially if it's used. It's a great emetic. What's emetic mean? They should throw up. So charcoal can do that, and therefore charcoal has been used for quite a while for poison, things like that. Are there any heavy metals in your alcohol? My gosh, if there is, what might be in your alcohol, especially if you drink Heineken or German beer? They have formaldehyde to increase the rate at which the things ferment. Oh, I know. So I've gotten to where I smell Heineken and I can smell the formaldehyde. I know that I'm looking for it. Okay. So honestly, I can't answer that question because I haven't done the research into it. But my gut instinct as a scientist is that it really won't work with alcohol. It might with other drugs or something that has some other kind of heavy metal in it. Okay, which you'd be surprised how many there are. Yes.
What are some other things you know about beers, like the formaldehyde and
That, you've just about extended that's about it. I am a wine person. I live in Davis, the #1 enology school in the world. So everybody there you sit in a restaurant and you learn about wine. I mean, you can't help it. So that's basically all I know, except I can't stand it. Sorry. Yes.
So I think that there's some diets going around saying like you remove all your carbs and you're able to like maximize weight loss. How do you feel like what is your
And I'm glad you asked this question because this really is the crux of so many conversations right now in the United States and in the Western world. And again, this is a first world problem, isn't it? And I am a third world, professional. So, but to answer that question for you, anytime I take a patient and put them on a routine, they're going to lose weight because most people aren't on routines. And what they need is a routine. If you ate nothing but ice cream, I put you on an ice cream diet. And I said, you can have half a cup of strawberry in the morning. You can have a full cup of vanilla at noon. And at night, you can have 3 cups of chocolate. That person is going to lose weight. You see what I'm getting at? I mean, if there's a caloric restriction, no matter what the food is, someone is going to lose weight. And for many people, it's simply being put on a routine and not just grabbing and eating unconsciously. It's conscious and mindful eating. And so once people start doing that, even with the diets that they have currently, people lose weight. So it is not a surprise to me that people who cut out all of something are going to lose weight. Yes, that's going to work. The thing you need to ask yourself that I do for my patients is, can you live on this the rest of your life? And if you can't, then you need to consider what you're doing is short-term for immediate reaction, which I have some patients who are sick enough that they need immediate, and I will put them on a liquid diet. I will put them on something that is slightly drastic for 2 weeks to stimulate the metabolism. But for most people, it's simply their diet, what they have, make a routine, or cut in half what you're eating. Half. Do you guys like this idea of being able to ask any question you want for a few minutes? Is that attractive to you? All right, well, we'll try to do this each class.